This program is brought to you by Stanford University. Please visit us at stanford.edu.
Tonight we want to we want to continue with the concept of curvature. I explained to you the idea of curvature for surfaces. Surfaces mean two-dimensional surfaces. Let me just review the basic concept. If you have a curved surface, you still have a concept of parallel transport. You have a concept of going as straight as possible, not deviating to the left, not deviating to the right. But nevertheless, the effect of the curvature will have an effect on the direction of vectors when they go around closed loops, when they go around closed curves, if there was some curvature in the area that they circumnavigated. So a sphere or any kind of curved surface, if we have a curved surface and we have a curve in that curved surface, I'm using curve in two different senses now. One has to do with the curvature of the surface, the other has to do with the curvature of a curve. Incidentally, a straight line is a special case of a curve. It's a curve which is uncurved. Yes, if you go around in a little closed path and you take a vector, start it somewhere on that closed path. Now, a vector means a vector that points in the direction in the surface. Roughly speaking, you can think of it as pointing in the direction of the tangent plane of the surface. So it points in the direction of the surface. That unfortunately looks like it's pointing out of the surface, but I can't figure out any way to draw a vector that it won't look like it's pointing out of the surface. So you keep in mind it's in the surface. And then we transport it parallelly to itself around the closed curve. If the region inside the closed curve is flat, then the vector will come back to itself. If there's some curvature in there, then typically it will undergo some rotation by some angle. Okay. That angle, let's call it theta. Now there are two senses of angle here that we have to keep track of. Question?
When you're talking about this curve, do you mean that it's the small curve? When you're talking about this curve, do you mean that it's the small?
I have in mind small curves, but
If they're large, you can have a lot of curves inside.
yeah, I'm speaking about small curves. We're going to be taking the limit of very small curves, infinitesimal curves, curves which contain infinitesimally small area. So we can concentrate on curves which are small by comparison with the radius of the whole thing. Okay, and that's the situation we're interested in. Curvature is a local thing. In other words, you can monitor the curvature by looking in some small little region and not going around whole big. You don't have to walk around the entire circumference of the Earth to discover that the Earth is curved. If you had sufficient accuracy, you could walk around a small little area and discover that the surface of the Earth is curved. Yeah.
So in this example, you have a surface, it's a space that's embedded in a higher dimensional space.
Yes, but I want you to forget that. I want you not to think about that. There's no. The problem. This is a problem of the architecture of our brains. We simply don't have the architecture to be able to envision surfaces and spaces out of 3 dimensions. So there's no way I can draw them.
Well, in that case, you have 1 dimension on top of 2 dimensions. So that's what he was saying, right?
I don't know.
Well, this one's 2 dimensional in a 3-dimensional space. And the curvature is actually the third.
Well, he's drawing a circle.
No. The thing is, that's exactly what we don't want to analyze. We don't want to analyze the curvature that's due to the fact that it's embedded in a curved way in the space. We want to ask the question, supposing a little bug lived on this surface. That bug can only receive light from inside the surface, can only see inside the surface, has no capacity to probe in the direction perpendicular, and can do all sorts of geometrical experiments involving little rulers but rulers which are attached to the surface, parallel to the surface, little protractors which also lie in the surface, and can do geometry on the surface without ever pointing their ruler or their protractor out of the surface. That's the term that comes up is intrinsic. In other words, properties which are intrinsic to the surface. The opposite are things that has to do with the way that it's embedded in space, and those are called extrinsic. Intrinsic and extrinsic. We are now interested only in the intrinsic properties that this very, very small bug would discover by doing experimental geometry on the surface with tools that can only lie in the surface. Okay? All right, so we're talking about the intrinsic curvature of the surface. And the idea of parallel transport is an intrinsic idea. If that little bug had wheels, think of a little bug with little wheels, little dumbbell-shaped affair, 2 wheels, that could roll on the surface. If the wheels had exactly the same size, and they couldn't, and of course I'm assuming that they cannot rotate relative to each other, then if I rolled it along the tabletop here, it would describe a straight arc, right? Okay. If I rolled it across the surface of a sphere, it would move as straight as possible along the surface of a geodesic, in that case, a great circle. So this is an experiment. Well, I suppose you'd say the wheels stick out of the surface a little bit, but we could make the whole thing smaller and smaller until the dumbbell bug here was infinitely small, and allow him to sweep out geodesics across the surface here. So the idea of a geodesic, and not only the idea of a geodesic, but the idea of parallel transport and the idea of covariant derivative are ideas which are intrinsic. Intrinsic, that bug could move around. Of course, we're really thinking about ourselves as bugs in 3 dimensions, and we're trying to disconnect the intrinsic properties of 3-dimensional space from the possibility that it might perhaps be embedded in some 4th dimension or something like that. Well, we wouldn't want to use rollers, but we could use gyroscopes. And gyroscopes are things which only point in our own 3-dimensional space. They don't point out into any hypothetical 4th dimension. And so exploring space with gyroscopes and rulers and so forth would be exploring the intrinsic geometry of 3-dimensional space. In any case, one of the things we can do with gyroscopes is we can define parallel transport. The gyroscope will naturally move in a way which moves parallel to itself, and it does define parallel transport physically. It has the same properties as the parallel transport that we describe mathematically. In any case, we can proceed to parallelly transport that vector from one point to another, and in fact around in a closed curve. When it goes around in a closed curve, it will not necessarily come back to the same configuration. What will happen to it is it will rotate in general. Parallel transport does not change the length of vectors. It changes only their orientation. It does not change their length. And so at most what can happen to a vector is when it comes around, it gets rotated by some angle. Okay. Now there are 2 senses of rotation that we have to keep track of. Senses, I mean now senses in the sense of sign, S-I-G-N. First of all, there's the direction that we go around the loop. We could go around one way or the other way. Depending on which way we go around, the vector will either shift in one direction or in the other direction. That's one sense of angle that we have to keep track of, which direction we circumnavigated around. We took our vector and we went around, let's say counterclockwise. The other angle that we need to keep track of is the amount that the angle deviates. So for example, if we go around counterclockwise and the vector, as it's transported around the curve, gets deflected in the counterclockwise direction, counterclockwise excursion produces counterclockwise rotation, then we say that the curvature is positive. If counterclockwise excursion produces clockwise rotation of the vector, we say the curvature is negative. But whatever the curvature is, it's a single function on the space, and it's simply defined by going around with your little probe, measuring, let's by definition say we go around counterclockwise, we measure the angle for very, very small curves here, the angle will be small. So let's just call it d theta, the small change in the angle when we go around the closed loop. And if we divide that by the small area contained in that closed loop, then we get the curvature. The curvature is the limit of the deflection angle, let's call it the deflection angle, divided by the area as the area goes to 0. Because as the area goes to 0, the deflection also goes to 0. That's called the curvature scalar, the curvature. And there's a curvature at every point on the surface. It can be positive, it can be negative. It's positive on surfaces that are spherical-like, sphere-like. It is negative on surfaces that are saddle-like, saddle-shaped-like. Now, the situation is clearly more complicated in higher dimensions. Let's first take 3 dimensions. In 3 dimensions, we can proceed around small closed loops, but we have to orient the surface somehow. For example, in 3 dimensions, I can go around a little closed curve here. I can go around a little closed curve here. I can go around in this direction. I need to describe an axis. The axis is not the axis of rotation of the vector. The axis is the axis around which my little bug travels doing his experiment. Right? So there's one axis in the problem, which we can just say is the axis around which the excursion takes place. Right? So our little bug, or our little gyroscopic setup, in this case, is transported around an axis. Now, in 3 dimensions, you can use the concept of an axis to describe a plane. It's just the axis perpendicular to the plane. In higher dimensions, or in lower dimensions, it's not useful to think of a little closed curve or a surface as having to do with an axis. It always has to do with 2 directions of space. You describe a plane by picking 2 directions of space, a direction over here, a direction over here, 2 perpendicular directions of space. Define a plane. It doesn't matter if you're in 5 dimensions, 10 dimensions, 20 dimensions. 2 directions, define a plane, and then you can go around in that plane. So you characterize the excursion that you go around by giving 2 axes. As I said, in 3 dimensions, you can replace the 2 axes by a 3rd axis, which is perpendicular to it. But that's special to 3 dimensions. All right, so that's one orientation that you have to keep track of. The other orientation, the other thing you have to keep track of is a vector taken around here will typically rotate, but it won't necessarily rotate about the same axis. If I take my apparatus, the gyroscope, my gyroscopic, I can take 3 gyroscopes all hooked together to define a coordinate system. Yeah. And I move them around and I see how they move, how they parallelly transport, and I take them around an axis, right, around the axis of my arm. if there's curvature in the region of my arm, when I go around to the other side, the axes will have rotated. What axis will these rotate about? Not necessarily the axis that you transported them about. For example, this might be the z-axis. I might take my little device here around the z-axis and discover that it rotated around the x-axis. So in diagnosing what's going on in space and understanding the curvature, there are in 3 dimensions, there are 2 axes to keep track of. In general, there are 2 planes to keep track of. The 2 planes to keep track of are, one of them is the little plane that you move around in. The other one is the plane in which the vectors rotate. Rotation within a plane. All right, so I'm going to write down now the general formula for... Yeah.
When we take this vector and we track around the surface and we come up with an angle that's different, that means that the concept of parallelism, which goes along with flat, is deviated from, which means that it's not flat.
Right. You discover that when you try to...
Can we run into the same problem with the concept of perpendicularity?
No. In principle, you could imagine that that does happen. That does not happen in Riemannian geometry. In Riemannian geometry, you can imagine more generalized kinds of geometries, affine geometries, other kinds of geometries. The notion of perpendicularity is an invariant notion in a Riemannian geometry. Things which are perpendicular stay perpendicular. All right, that's an important point. That parallel transport in Riemannian geometry and in general relativity is defined in a way that vectors, when you transport them, if they are perpendicular to begin with, they stay perpendicular. So perpendicularity is an invariant concept. Okay, so let's write down the general formula. Supposing, now I'm not even going to tell you how many dimensions we're in, because it doesn't matter. It could be 2, 3, 4, 100,000. It doesn't matter. Pick 2 axes. Let's see what I called them. I called one of them x nu and the other one x mu. And now what we're going to do, and there are 2 different axes. Mu and nu are intended to be different here. It could be x and y, it could be x and t, it could be whatever you like. We're going to go around in a small rectangle, or as close to a rectangle as we can build. In other words, we're going to have a small dx mu and a small dx nu. That characterizes the excursion in the x mu, x nu plane. We go a little bit along x mu, then we go a little bit along x nu, then we come back along x mu, and then we come back by the same amount along x nu. That creates a little bit of area, and that area will be proportional to the product of dx mu times dx nu. It won't be exactly dx mu times dx nu, because I haven't particularly said that these 2 directions are perpendicular, and I haven't told you what the metric is. But whatever the metric is, the area in here will be proportional to dx times dx, dx mu times dx nu. The area will be proportional to that. And so to begin with then, we have 2 axes and a little bit of area in there. We carry a vector, we start a vector at one end, and we bring it around, and we look at it, what it's done. Now, what are the rules? The rules are we do it by parallel transport, which we've already defined. We'll come back to that definition, but it's the definition involving the Christoffel symbols. So we parallel transport that vector around the curve, okay, bringing it back to itself. Parallel transporting it means that the covariant derivative along the curve is 0. So you would think it must come back to itself if the covariant derivative is 0. But the thing is, the covariant derivative is not the ordinary derivative. And so if we start with a vector v, and we transport it around the closed curve, there will be a change. And that change, let's write down a very general formula. It will be proportional to dx mu and dx nu. Why? Because we expect it to be proportional to the area that we've enclosed. So it will be proportional to dx mu and dx nu.
You want to use mu on the superscript for v? Because you already used mu.
Oh, you're right. We shouldn't. Dx nu, dx sigma. Good point. We shouldn't. So it's going to have dx nu and dx sigma, the x nu, all right? It is going to also involve the vector that we started with. It's basically going to be a rotation of the vector. The change in a vector will be proportional to the vector that you start with. If you start with a vector which is 0, it'll stay 0. If you start with a vector which is very long, it'll stay very long because its length is preserved. And so we expect that the change in the vector when it goes around the closed curve will involve the vector itself. Let's give it an index v tau. And the rest has to be some object which defines the curvature. It's the curvature tensor. So let's see if we can build a formula. We have 3 indices upstairs, 1 index on the right-hand side, 1 index upstairs on the right-hand side, on the left-hand side here. The only thing we can have here is some tensor which has an upper index mu to match this index here, a nu and a sigma and a tau. All right, now you can work this formula, you can work this out yourself. All you have to do is use the formula for covariant differentiation. Say that along the first curve, let me write it down. Do you remember what the formula for covariant differentiation along a curve is? Let's just write it down. It's something like dv mu by ds, s is length along the curve, plus gamma mu, I don't know, alpha beta times the v alpha times the tangent vector dx beta by ds. That was the covariant derivative of the vector v along the curve parameterized by s. Okay. If I want to set that equal to 0, then I have an immediate formula for how v should change along s, how the components of v should change along s. I don't need the ds here. The ds is not playing any role. Just divide through by it. What it says is that the change in the vector v going from here to here is equal to minus gamma alpha beta mu v alpha dx beta. That's the formula for the change of the vector in going from here to here. Now, what do you think the change in the vector would be if I parallelly transported it to here and then parallelly transported it right back? The answer would be 0, no change. Parallel transport is not so weird that when you transport a thing and then transport it back, yeah, it doesn't do anything. You need some area enclosed in order to get an answer. All right, so if you transport from here to here, you get that. When you transport back, you're going to get something entirely similar, except along a neighboring curve. It's not going to be exactly the same. Why not? Because the Christoffel symbol over here and over here are not exactly the same. They vary a little bit. Also, when you go from here to here, the change in V does not cancel the change when you come back along this arc of the rectangle. Why? Because the Christoffel symbol varies from here to here. Okay. So because the Christoffel symbol varies as you move around, by the time you get back, the changes, which is this V mu, the change in V mu is not equal to 0. In fact, it's clear that what's going to come into it are derivatives of gamma. It's the derivatives of gamma, the fact that gammas vary from place to place, that means that you don't cancel out deviations along one arc by deviations along the arc coming back. Here's the formula. I haven't told you what R is yet. But you can see that in order to get something, you have to have a shift along one axis and a shift along the other axis. So it has to have a dx times another dx. That's clear. You have to enclose a little area. The change in V will always be proportional to V itself. So even when you go around the closed loop, it's going to be proportional to V itself. And what would you expect R to be made out of? From what I just told you. The derivatives of the Christoffel symbol. The derivatives of the Christoffel symbol are going to enter into R. This is a tensor equation. dx, V, delta V on this side here are these are all, or this is the difference of two vectors at the same point. Those, delta V, difference of two vectors, vector and a slightly shifted vector. This is a tensor equation, and this is the curvature tensor. It's the Riemann curvature tensor. And what it tells you, as I said, is per unit area, it tells you how a vector changes when it goes around in a closed loop. In fact, it rotates. The vector rotates. But even if it did something more complicated than rotating, this would be the formula that you would use. And that's what the curvature tensor is all about. It tells you how vectors fail to return to their original direction when you parallelly transport them around a closed curve. Indication that there's curvature somewhere inside. Okay, now notice that two of these indices here, nu and sigma, have to do with the plane that you moved around in, the x mu and the x sigma. The other two indices, tau and mu, have to do, they contract, or they have to do with the indices of V itself. Tau over here goes with tau over here, mu over here goes with mu over here. So two of the indices have to do with the directions in space that you go around, and the other two indices have to do with the vector themselves and tell you how it changes. All right? So that's the pattern. That's the structure of the curvature tensor. Not the structure of it, but that's what a curvature tensor is. It's the general definition of the curvature tensor. And as I said, it always has four indices, two of them telling you about the plane that you're moving around in, and two of them telling you about the plane of rotation of the vector. That's why it has four indices. Two to tell you what the directions you're moving around in, and two to tell you the plane of rotation, if you like, that the vector undergoes. Those are the four indices of the Riemann tensor. This is the Riemann tensor. And I'm now going to write down, it's too tedious to derive this. I've given you the principles. You know how to parallelly transport a vector around a closed curve. You could make your closed curve be a little rectangle. You could carry out the process and find R. And I advise it. It's a nice exercise. It's not too hard to do. I'm just going to write the answer down because it's more than is appropriate to do on a blackboard in 10 minutes. But the answer is not hard. I memorized it years ago, and no, I could write this in my sleep. Okay, so let me write down the answer for you. The Riemann tensor with index rho upstairs. Notice that the way I've defined it, it has one index upstairs and 3 indices downstairs. Of course, you can change that. You can lower an index of a tensor by contracting it with the metric. But the way that it's been defined here, from the definition here, it has one index upstairs and 3 indices downstairs. And for some reason, I have used different letters, but it doesn't matter. Sigma, mu, nu. Same tensor, except I've rearranged the indices, and I'm going to write down what they are. They're in terms of derivatives of the Christoffel symbols, and also products of the Christoffel symbols. d mu and then there are two terms which are just products of the gamma mu lambda rho gamma nu sigma lambda minus gamma nu lambda rho gamma mu sigma lambda. Okay. That's the Riemann tensor, and as I said, it involves derivatives of the Christoffel symbols, and it's not hard to work out. That's it. Any questions up till now? You know it's a tensor. You actually know it's a tensor from its definition. You know it. Well, how do you know it's a tensor? The left-hand side. First of all, how do I know that the left-hand side is a vector? It's a difference of two vectors, and it's kind of like a derivative of a vector, isn't it? But a derivative of a vector is not a tensor. The covariant derivative is a tensor. But that's because the coordinates may vary from place to place. If we're comparing two vectors at the same place, at the same origin, then the difference of vectors is a vector. It's only when we're trying to compare vectors at different places that the difference between two vectors, or the derivative of a vector with respect to position, may not be a true vector itself. When we're comparing vectors at the same point, in other words, subtracting two vectors, each of which refers to exactly the same point in space, that is a vector. Okay? So the left-hand side is a vector, transforms as a vector. dx sigma, dx nu are vectors. V by definition, by assumption, V is a vector. And if an equation like this is true for any vector, the assumption here is that this equation is true for any vector that you start with, that when you take it around the closed curve, that this is what you get. If you have a vector equation such as this is a theorem. If you have a vector equation like this, which is true for every possible vector that you can start with, then R must be a tensor. So there's a theorem involved here that R is a tensor. It's not obvious from here.
Is the second half of that some kind of a commutative?
Yes. Indeed it is. Yes. If you think of, all right, so let me tell you what it is. It is some kind of commutator. think of these indices as being matrix indices with a parameter nu over here. All right, then you could, here's a matrix, here's another matrix. Let's see, do I have this right? Mu, wait a minute, did I write this correct? Rho, yeah. You can see here that there's a product of matrices. The index that's summed over is lambda here. Right? And so you could think of this as the product of two matrices, one that you could call gamma mu, and the other that you could call gamma nu. There's hidden indices in here because each one is a matrix. This one is exactly the same, except it's minus gamma nu times gamma mu. So this is, in fact, the commutator of two matrices. Right. And in fact, the whole thing is also a commutator, but that's a little more complicated. It's a commutator of two covariant derivatives.
Is it obvious that this does not depend on the directions you took? You started with the x and the x nu and x mu?
Well, it does depend, but it only depends through the product dx times dx. We're imagining two different vectors here. We shouldn't call this dx. We should be more careful here. These are just two different displacements, dx with an index nu and dx with an index mu. Two different displacements, one over here, one over here. We might have called one of them delta. We might have called, in fact, we might have done it this way. We might have defined displacement over here, which is delta x, and another displacement over here, which is dx. Then we would have put one delta x and one dx. I'm not sure if that helped. But it's proportional to the product of the two displacements.
Aren't those both summed over? Those are both summed over.
Yeah.
So they'll take on all values.
Yeah. They're both summed over.
Question?
Yeah.
Can you illustrate what it means to keep a vector parallel to itself when you move in a curved surface, like on the surface of the Earth? I have a vector that's parallel to the surface. How do I know that I'm keeping it parallel to itself as I move along the surface of the Earth?
Well, as I said, along the surface of the Earth, it's easy. You just drive straight ahead. You aim your steering wheel straight ahead. You don't care, and you don't allow yourself to turn it. You don't care whether there are bumps or curves in the surface. You don't care whether you're going over mountains, through mountain passes. You keep that steering wheel dead straight ahead. And that is the definition of a geodesic. In other words, locally, in small little patches, you go perfectly straight ahead. Now, the technical definition is you find coordinates locally which are as flat as possible, which means that all of the first and second derivatives of the metric are equal to 0, and in those coordinates, the vector is constant, the derivative of the vector is equal to 0. So the technical definition is in terms of coordinates which are chosen to be as close as possible to Cartesian coordinates, first and second derivatives of the metric all equal to 0. In that case, the only variation of the vector will come from the variation of the vector and not the variation of the coordinate frame, if the first and second derivatives are all equal to 0. Okay, look.
So if I move along a geodesic and the vector moves with the curvature of the geodesic, that's parallel.
If you have a geodesic and you have a vector which is pointing along the geodesic, it will stay pointing along the geodesic. Right? If you have a vector which is perpendicular to the geodesic, it will stay perpendicular to it. All right? Now, that's not enough. In 2 dimensions, that's enough to tell you exactly what covariant differentiation means. In 3 dimensions, it's not, in particular along a geodesic. The problem in 3 dimensions is you might have a geodesic. Anything which is along the geodesic will stay along the geodesic. But something which is perpendicular to it, it's not enough to know that it stays perpendicular to the geodesic because it could spiral around it. So it's a little more complicated what you can do in higher dimensions is you can do the following trick. You can take 2 neighboring geodesics, take a point, and draw a geodesic through it. Let's first think about it in flat space. If I have a geodesic pointing through my shoulder here, there's another geodesic that also points through my shoulder. There's many of them, of course. But take another one which is almost parallel to the starting one, just slightly shifted at a different angle. All right? Those 2 define a plane. Okay? Now, if I transport a vector along the geodesic, not only will it stay perpendicular, not only will it stay at the same angle to the geodesic, but it will stay at the same angle to that plane which is defined by 2 neighboring geodesics. Is that clear in flat space? Yeah. Okay, that almost becomes a definition in higher dimensional space. You take, it could be used as a definition. You take another neighboring geodesic. Now, neighboring means infinitesimal angle relative to it. They define a plane in here. And as you transport along one of the geodesics, the angle relative to that plane, something which is perpendicular to that plane, stays perpendicular to the plane. So you can do better in higher dimensions with a family of geodesics which all pass through the same point. But of course, you don't want to take geodesics at wild angles. You want to take almost parallel. That gives you a good definition. That gives you another definition of parallel transport. Okay, but it does come down to the same thing. In a frame of reference which is locally as flat as possible, it means that the vector has no derivatives in that frame at that point. All right, now this is, as I said, this is the definition, the geometric definition of curvature. It's a complicated definition. The concept may not be so complicated, but the actual mathematical formula for it is, as you can see, rather complicated. How many components does the curvature tensor have? Let's say in 4-dimensional space-time. Well, yeah, 4 times 4 times 4 times 4. It's not that bad. It's not that bad because there's a lot of symmetry. There are a lot of redundancies and a lot of symmetry that you can read off this formula. You can read them off this formula. To see the symmetries best, it's best to lower this index. I can lower this index the usual way. Supposing I wanted to define R lambda sigma mu nu, I just multiply by G lambda rho times R rho sigma mu nu. All right, you can lower and raise indices using the metric, and so there's nothing special about one index being raised here. I can lower them back down so that they're all lower indices. It's still called the Riemann tensor. It's the Riemann tensor with all covariant indices. It's in this form that the symmetries are simplest, the symmetries of this object. All right, so if you work them out using the definitions of the Christoffel symbol, and it's not hard, but it's tedious. It's a little bit tedious. There are simple ways to do it, but they all involve a degree of sophisticated notation, which would take us beyond what I want to do in this quarter. Forms and other fancy tricks.
Question. Yeah. For the d theta dA equals R, is theta dependent on the direction of the
Yeah, theta is dependent on the direction you go around. Go around one direction, you get theta being plus. If you go around the other direction, you get theta being minus. Yeah, the sign switch. And it's the relationship between the signs of going around and angle rotating which tells you whether the curvature is positive or negative. Right. And all the components of this the curvature tensor can be either positive or negative. Some of them can be 0. Some can be 0 and others not be 0. That's quite possible. Okay, so let me tell you what the symmetries are. Let's see. First of all, let's remember it's the two middle indices here which have to do with the plane that you go around in. The two middle indices parameterize the plane that you move around in, the new sigma plane. The mu and tau indices, if I'm not mistaken, let's see, do I have this right? Let me just check it. Yeah, the two middle indices have to do with the plane that you go around in, and the two outer indices have to do with the directions of the vector itself, how it rotates. Okay, so same is true here. These two indices have to do with the plane that you move around in, the two inner indices. All right. All right, I'm going to write down the symmetries. I hope I have them right. First of all, it's antisymmetric with respect to interchange of alpha and beta. All right, that just says if you interchange alpha and beta, it's antisymmetric. It's also antisymmetric if you interchange gamma and delta. So it's also equal to minus R alpha beta, the original alpha beta, delta gamma. Antisymmetric with respect to these two, and antisymmetric with respect to those two. That's one thing. And the only other important thing is that it's symmetric. Yeah, it's symmetric with respect to taking these indices and changing them, interchanging them like so. In other words, this is equal to R gamma delta beta alpha. No, gamma delta alpha beta. Now, these are not going to play any big role in what we do. I'm just putting them down for completeness. The point is that there are a lot of relationships between the components. There aren't as many as it looks. There's a lot of symmetries between them, just following from the definition in terms of the Christoffel symbols and in terms of the symmetries of the Christoffel symbols. I believe there are 24 independent ones. That's a lot. So when you start doing calculations in general relativity, it's awful. No, they are unpleasant.
Is it the sign of the permutation in S4?
What's that?
Is the sign the same as whatever the permutation is in the symmetric group?
No, I don't think so.
So that if you interchange beta and gamma, it doesn't become negative?
Well, let's see. I've given you all of the symmetries. Now we would have to, if you interchange gamma and beta, I don't think so. I don't think there's any special symmetry. Let's see, I'll tell you how many components there are in 2 dimensions. Let's make a table, and then you can tell me whether it's anything special. Dimension 2, dimension 3, and dimension 4. I have no idea what the answer is in dimension 5. I would have to work it out. I can work it out. But in dimension 2, there is 1 component. In dimension 3, there are 3 components. And in dimension 4, there are 24 components. Does that strike any bell? They are equal to factorial. No, they're not. 3 is not a factorial. No.
When you switch the rotation around the loop, you get a minus sign, don't you?
When you do what?
When you go around the loop in the opposite direction from the way that you...
Yes, you get a minus.
That's the same as interchanging.
Yeah.
Okay.
Yeah.
Well, those are the middle two, right?
Oh, God, I hope I don't have the indices mixed up. Oh, brother. You know, I think I do. Those are the middle two. Let's see what I have here. Let me just look at it for a minute. Rho is up here. No, I definitely have something inconsistent here. It's, yeah. Yeah, and those have to do with the two directions that you move in. Mu and nu, all right. These two terms here have to do with the fact that the Christoffel symbols vary along the mu and nu direction. So these two, mu and nu, those are the two that have to do with the directions here. I think I made a mistake. This does not look right to me. Let me correct it. Yeah, I think this should be R sigma nu mu tau v tau. I think I think I have a misprint, a typo in my notes, because you are right that this is clear. Yeah, it's quite clear. This is antisymmetric under interchange of mu and nu. If I interchange mu and nu here, these two will be the same except for a minus sign. So it's antisymmetric under mu nu interchange. Is that what I said? Yeah, this is antisymmetric under mu nu interchange. Antisymmetric. It's also antisymmetric under lambda sigma interchange, that I know for a fact. And it's symmetric with respect to interchanging lambda sigma and mu nu. So do I have it right? I think that's what I wrote here. I think that's consistent with this, isn't it? Let's see. Antisymmetric with respect to these two, yes. Antisymmetric with respect to these two, yes. And symmetric with respect to moving them in pairs. That's correct. And somehow what I wrote down here originally was incorrect, so let me correct it. It should be R with a mu. Let's call it sigma. Yeah, R. Yeah. I think I have it right now because delta x tau. Yeah. Shall I go back a step and you want to go through it again?
Here's another question.
I didn't think so.
Question?
Yeah.
If we were talking about the Riemannian for the surface of the Earth,
Yeah.
would that be dimension 2 or dimension 3?
Dimension 2.
Okay, and then, so there's one number. Is that the radius of the Earth?
Yep. Curvature, the numerical curvature is the inverse square of the radius of the Earth. The smaller the Earth is, the larger the curvature.
You don't have to know where the center of the Earth is.
In the case of a sphere, you don't have to know where. Okay? In the case of a sphere, you don't have to know where. And for a sphere, the curvature is just equal to 1 divided by the square of the radius of the sphere. The smaller the sphere, the bigger the sphere is, the closer it is locally to being flat. So the bigger the sphere, the smaller the curvature. The smaller the sphere, the bigger the curvature. Yeah. Yeah.
How do you know that the loop actually does close upon itself? Is it just that the transform works out, or there's some other way to check? When you take your little loop
Yeah.
that encloses the area,
Yeah.
how do you enforce the fact that you do in fact close the loop?
Well, you describe a little curve that comes back to itself. I'm not sure how to, you invent an x of
Put an X on the ground.
sigma such that x of sigma is equal to x of sigma plus a little bit. So you invent a function for each one of the components. You invent functions which come back to themselves after a small excursion.
Well, it just looked like when you picked those two directions,
Yeah.
like coordinates, you could imagine that if you went, followed coordinates, you wouldn't get back to where you started.
That's in fact true, but what you're saying is if I took a vector over here and then took another vector over here, then parallelly transported this one up to here, that it wouldn't quite close. And that's true. But the failure to close would be a second order thing, which would be quadratic in the dx's themselves. And so the failure to close would be, you would have to correct this a little bit to make it close. But the amount that you have to correct it by wouldn't affect any of this. It would be a small correction that would also be proportional to the area.
Basically, what we're doing here is we're proving that some of the internal angles is not 360 degrees if it's curved. Yeah. Because 90, 90, 90 is perfect flat.
It occurs to me, the fact that this doesn't quite close is connected with these terms. Yeah, it's connected with those terms. Why are those terms there? They're there just because the rectangle doesn't close.
So can you look at it therefore as a departure from it transforming like a tensor, and whatever that departure is basically tells you?
Yeah, you can think of it that way. There is another, for those who are mathematically minded, I will give you a very, very simple definition of if you're a little bit mathematically minded, then there's the covariant derivative with respect to x mu is defined how? It's derivative with respect to x mu plus gamma mu dot whatever. And it acts as an operator, as a differential operator on vectors. It's a thing which acts on vectors. It's a differential operator, contains derivatives, and it contains multiplication by gammas, which are also matrices and act as matrices. The curvature is defined in terms of commutators of covariant derivatives in different directions. Covariant derivatives in different directions don't commute with each other, and the curvature is defined in terms of that. Now, that's too abstract a definition for our class. For our class, it's just geometrically the small change in a vector when you go around a closed loop. It contains the derivatives of the Christoffel symbols, and it contains quadratic things in the Christoffel symbols. And the reason that it contains Christoffel symbols is because it's Christoffel symbols that determine how parallel transport works. How a thing gets parallelly transported from one point to another depends only on the Christoffel symbols. So that's the only thing that it could involve. And derivatives of them. Okay, so that's a definition that's worth committing to memory if you're interested in the subject. And I honestly don't really know any way to make it simpler than that. I simply memorized it, worked it out a few times for a sphere, for a cone, for a couple of geometries, for a three-dimensional geometry, and after a while you get familiar with it. And it's not as remote an idea. But again, what it has to do with is intrinsic properties of the geometry that are obstructions to its flatness, and to diagnose it, you go around in little closed paths and you see how things change under a circumnavigation around a little closed path. All right, more definitions. They give you these definitions now because they come into general relativity in an important way. The geometry of them is obscure. They're not particularly easy to understand geometric quantities. There's something called the Ricci tensor. The Ricci tensor doesn't have 4 components, it has 2 components. In that sense, it's easier than the Riemann tensor, but the only way to get the Riemann tensor is to know the Ricci tensor first, and it's gotten from the Ricci tensor by taking the upper index here, mu alpha nu, and contracting it. What we're doing now, let me remind you, 2 of these indices have to do with the 2 directions that you go around in. The other 2 indices have to do with the rotation plane. If you take 1 index having to do with the circumnavigation and 1 index that has to do with how the vector rotates, and you contract them, you get what's called the Ricci tensor. To try to fathom it geometrically is very hard. There's nothing easy to picture about it. If you like, it is simply a tensor that you make by contracting. You can write it in another way. You can write it in terms of the tensor with all of its indices. Let's write it with all of its indices downstairs. Alpha, beta, gamma, delta. Then you contract index alpha with index gamma by the metric, G alpha gamma. Alpha with gamma, you contract them together, sum them, and you have a thing which only depends on beta and delta. It has no simple geometric picture that I know of. It's made out of the Riemann tensor, but it has only 2 independent components. It has only 2 components, not 2 components, 2 indices, and it's symmetric. The symmetries of the Riemann tensor assure that this is symmetric. So this is also equal to R delta beta. That's the Ricci tensor, and it plays a very, very big role in the dynamics of gravity, even though it is not. I suspect the reason it took Einstein 10 years to work out general relativity was in finding the Ricci tensor, because it doesn't have any simple pictorial significance. In any case, it is what it is, and it will play an important role in what comes. Ricci? R-I-C-C-I. How else would you spell it?
Depends on what language it is.
What was Ricci's problem that he had to come up with?
You know, I don't know. You know, I've looked that up several times and I could never find out. I don't know. Okay. No, I'll tell you. Yeah, in 3 dimensions, Ricci was interested in 3-dimensional space. In 3 dimensions, the Ricci tensor and the Riemann tensor are completely equivalent to each other, and I'll tell you why. It's very simple. In 3 dimensions, a plane is in 1-to-1 correspondence with an axis. So if I have a thing which depends on a pair of planes, that's 4 indices altogether. That's 4 indices, 2 for each plane. Because a plane is the same as an axis perpendicular to it, it can also be thought of as a thing which depends on only 2 vectors. So a thing which depends on 2 planes in 3 dimensions can be thought of as a thing which depends only on 2 vector directions. The Ricci tensor is the way of describing the Riemann tensor when you describe it in terms of axes instead of planes. It takes 2 directions to define a plane, and so 4 directions to define a pair of planes. But in 3 dimensions, it's simpler. It really only takes 2 axes. So I believe that Ricci discovered this form of it when he was working in 3 dimensions. Why it turns up to be so important in the theory of gravity, we'll come to that, but it's not because it has any easy-to-picture geometry to it. Okay, we've covered the idea of curvature as much as I can cover it in one hour. Geometry is half of the theory of gravity. The other half of the theory of gravity is matter, mass. Mass affects geometry. Mass curves geometry. John Wheeler used to like to say, he had a phrase, a slogan, mass curves geometry, and geometry tells particles how to move, or something like that. I don't remember. It was more elegant than that, but the idea being that the presence of mass affects geometry. That's another way of saying the presence of mass creates gravitational field. And gravitational field affects the motion of particles. So they affect each other. Particles, masses affect the gravitational field. That means that they affect geometry. And geometry affects the way particles move. The curvature, incidentally, is as we'll see, is the analog in general relativity of tidal forces in Newtonian gravity. It's the thing that you can't remove. It's the obstruction that you can't remove by a coordinate transformation. So think of it that way, and we'll see more clearly how it works as we go along. All right, I want to define some notions which are important, not only in general relativity, but in field theory in general. We've talked about them in earlier classes. Let's begin with electric charge. Electric charge is a typical thing which can flow, which has a density, which has a flux. A flux means a current of it, and which is a material quantity that has a sense of being a substance, if you like. All right. First of all, let's take a box of space, small box of ordinary space now. This is not space-time. Not space-time. I'll tell you when it is space-time. Not space-time. Just ordinary space. And now let's imagine the world is full of charged particles, tiny, tiny charged particles, smoothly distributed. And I can ask, what is the total charge in the box? The total charge in the box, total electric charge in the box, let me call it, since the box is going to be taken to be small in the end, I'll call charge, Q is charge. The amount of charge in the box we'll call dQ, because the box is small. And of course, it will be proportional to the volume of the box. But if I divide, let's call the volume of the box, let's call it dV. A small box, infinite small box, divide the charge by the volume, and I get the density. Let's call it rho. Now this is the density not of mass, but the density of charge. So I'll just put a little Q down there to remind you that it's the density of charge, not the density of mass. That's, if you like, the definition of charge density. It's go to a particular point, take a small box, take the total amount of charge in it, divide it by the volume, shrink everything to 0, and the limit is the density. It follows, of course, that the total charge in a finite box is the integral of the density over the box. So that's charge density. Let me picture it another way. I want to now picture it in a four-dimensional picture. Unfortunately, I can't draw four-dimensional boxes very well. So what I'm going to do is think of the three-dimensional box as being two-dimensional. Here we are going to draw space-time. Here's time, here's space, x and y. And unfortunately, I can draw another axis, but it would only make things a little more complicated than they need to be. So let's imagine another axis, but not draw it. What does this box look like? It just becomes a little square in space, a little square. It's not really a square, it has 3 dimensions, but due to the limitations of the blackboard and our brains, I will simply draw it as a little square with 2 directions, x and y, and implicitly a 3rd direction. Now, there are charged particles. Charges don't disappear. Charges are conserved. A charge moving around in the space-time is just a world line that never begins and never ends because charges don't come and go. And now we can imagine asking how many charged lines, how much charge passes through this box. That's just another way of asking, at a given instant of time, how much charge is in the box. How much charge is passing through the box in a space-time sense is equivalent to the question how much charge is in the box at a given instant of time. We could follow the box, of course. We could follow the box in time. Here's the box, same box a little bit later. Is the charge in that box necessarily the same? No, because charge can enter the box over here, but then go out here and not pass through the upper box. That's just another way of saying that a charge can move out of the box. Right? So charge is conserved, but that doesn't mean the amount of charge in the box, in a particular box, stays the same. All right, so that's the notion of charge in a box, charge density, and here I've drawn the charge density in a way that makes it seem as though it has something to do with charges going through a box. All right, so that's rho. Now let's talk about the current, the electric current. The electric current is a similar kind of idea. Now we're going back to space. Let's go back to space and forget space-time for a moment. And let's draw a square. Now I don't mean a 3-dimensional box. I mean a 2-dimensional box. A window. Think of it as a window. There's no windows on the wall here, but think of it as a window. And think of the actual motion of charges as they move and pass through the window. Some charges will pass through the window, some charges will not pass through the window. Take the charges which pass through the window. How much charge will pass through the window? Well, it's going to be proportional to the area of the window, but what else? What else might it be proportional to besides the area of the window? The time, the amount of time. All right? So there's a flux of charge, and the amount of charge through the window per unit time is related to what's called the current. So let's write that. The amount of charge that goes through the window, and I'm going to call the window now a small window with a differential area dA per unit time. What do I call that? I'm going to call that the current. But this area has an orientation. The area has a normal vector to it. So I'm really talking about the charge, for example, flowing in a given direction through a window perpendicular to that direction. It's got a vector index attached to it. So for example, if this is the x window means a window in the yz plane. If this is the x window, the charge going through the x window per unit time is called Jx. It's called Jx. J is the symbol for current. It's called the current. You can call it the flux of charge, the current of charge, the flow of charge, whatever you like. But it's the charge through a window perpendicular to x in per unit time. And likewise for jy and jz. If you want to know what jy is, you take your window oriented perpendicular to the y-axis, and you ask how much charge is going from the negative side of the y-axis to the positive side of the y-axis per unit time, and that becomes jy. Right? Now notice both rho and j are charges per unit. How do we say this? How many powers of a length does a volume have? 3. Now remember that time and length are measured in the same units. We are going to set throughout the speed of light equal to 1. Time has units of length. So how many units of length are in the denominator here? Also 3. The only real difference between these is here I have charge per unit 3-dimensional space-like directions. Here I have charge per 2 space-like, 1 time-like direction. So these are clearly closely similar kinds of things, charge per unit length cubed, if you like. You can think of the window as being the window persisting for a length of time t that has an area, delta x times delta y, but a duration of time, delta t. You can think of it as being like a volume, a 3-dimensional volume, but a 3-dimensional volume with one of the directions being time. So both the flow of charge and the density of charge are components of a single thing. A single thing of a flow of charge through various kinds of windows. This window is a space-space-space window. This window is a space-space-time window. There are no windows which are time-time-space because there's only one direction of time. So this is all the kinds of windows there are. And these objects form together to form a 4-vector. It's natural to group them together into a 4-vector. And that 4-vector is called the current, the 4-dimensional charge current. You group together rho, jx, jy, and jz. And those you just call j mu. In other words, the charge density becomes the time component of a 4-vector. The other 3 components are characterized by the direction of the flow of charge. And if charges are just sitting still, it's as though they're moving in time, if you like. You can think of it that way. A thing which is sitting still is still moving through space-time, and it's passing through these windows in space-time. And so rho together with j form a 4-vector of current. Now I'm going through this rapidly because we did it last quarter, the idea of the 4-vector of charge. How do we express the notion of charge conservation? The continuity equation. Everybody remember the continuity equation? I'll remind you what it is. The continuity equation is the basic equation. I don't want to erase this. I want this there. It's the basic equation which tells us a little more than just that charge is conserved. If charge is conserved in the whole universe, it just says the amount of charge in the whole universe doesn't change. But there's a little more to charge conservation than that. I've explained this to you more than once. We'll do it once again, though. If a charge disappeared over here and reappeared on the moon, then instantly we would say charge was conserved, but an experiment taking place in this room would be clearly deceived into the idea that charge is not conserved. It doesn't really work that way. We don't get deceived into the idea that charge is not conserved for some reason. And if you don't like the Earth Moon, you say, well, we could always do experiments involving the Earth and the Moon. Make it the Earth in Alpha Centauri or the Earth in the next galaxy over, whatever you like. it's quite clear that charge conservation by itself really doesn't have any real implication for experiments done in finite volume. The real notion of charge conservation is what's called local charge conservation. It doesn't mean that the amount of charge in the room doesn't change. It means that any change in the charge in the room is due to observable flows of charge through the walls. The only way the charge can change in the room is if it flows through the walls. So an increase in charge would correspond to a flow of charge in. A decrease of charge in the room would correspond to a flow of charge out. What mathematical object is there that could represent the flow of charge radially outward from a point? The divergence. The divergence is the mathematical quantity which expresses the idea of a flow outward. So if you take a small region of space and you ask how much charge is in it, or not so much how much charge is in it, but how does the charge change with time? Well, the charge that's in that small region is the volume of the small region. Let's take the volume to be fixed, and let's set it equal to 1 for simplicity. Then the charge in that small unit volume is rho. I could multiply it by the volume, but I'm setting the volume equal to 1. In any case, I'm going to hold it fixed. All right, now how does that charge change? Well, it changes by charges going into and out of the room, but let's take the time derivative of it. If there's a time derivative to the charge density, it must mean that there is a current at the boundary. But that current, for example, a uniform current flowing straight through in the x direction, that would do nothing because there would be as much current coming in from one side as going out the other. It's the divergence of the current which tells you the charge, net charge, is passing out. So if the charge is increasing, then that must mean charge is coming in. It must mean the divergence is negative. The right equation is that the change per unit time of the charge density plus the divergence of the current. Now this is the three-dimensional current, Jx, Jy, Jz, must be equal to 0. What it expresses is that the rate of change of charge in the box is equal to the negative of the amount of charge that's flowing out of the box. If the charge is flowing out of the box, the amount of charge must be decreasing. We can write this explicitly. It says that, let's say, partial of rho with respect to t. The partial of rho with respect to t. And then what is the divergence of the current? Anybody remember the form for the divergence of a vector? Right. It's the derivative with respect to x of the x component plus the derivative with respect to y of the y component, jy, jy, plus the derivative with respect to z of jz, and that's equal to 0. But if I now call rho the time component of j, we can just write this as j naught, the time component. And we can call t the time component of the 4-vector of position. This becomes x1, 1, 2, 2, 3, 3. In other words, the continuity equation just becomes the very simple, nice-looking equation that the derivative of j mu with respect to x mu is equal to 0. Summed over mu. Two basic kinds of definitions: definition of current and density, and the continuity equation. That's the basic ingredient that goes into the conservation of electric charge or any other kind of charge that's conserved. Okay? Now, one thing about charge is that charge itself, the components of a current of charge are a 4-vector, but the charge itself, how about the charge itself? Supposing I have, well, what are the units of charge anyway? Coulombs, huh? Yeah, Coulomb is a huge amount of electric charge. If you could somehow assemble a Coulomb of charge on this table, you would want to get far out of the room because, okay. Supposing I say there's a Coulomb of charge on the table over here. And supposing you're moving by on a railroad train, how much charge would you say is there? Coulomb. Charge is an invariant. It's a scalar, if you like. Charge is a scalar. The charge current is not. The charge current and density are not scalars, but the charge itself, the total amount of charge that's there, is a scalar. And so you should...
Were you afraid of a Coulomb of charge?
What's that?
Why were you afraid of a Coulomb?
Well, that's so much charge that the repulsive force, here's what I mean. A Coulomb charge is what, about 10 to the 19th? I think it's 10 to the 19th electrons, if I remember. Okay, so you say, okay, you have 10 to the 19th atoms. 10 to the 19th atoms has 10 to the 19th, hydrogen atoms, has 10 to the 19th electrons. Who's afraid of 10 to the 19th atoms of hydrogen? But now take those 10 to the 19th atoms of hydrogen and remove the protons. Then you have 10 to the 19th electrons, and that is a highly explosive situation with all the electrons repelling each other. They would repel each other and just make a huge explosion.
I had no trouble putting that amount of charge in a 1 farad capacitor on your desk.
A whole Coulomb?
Yeah, opposites.
No.
They're close together.
I have no trouble putting it in a 1 farad capacitor on your desk, and I can go to Fry's and buy it.
No. Yeah, that's right. Yeah, you have a positive and negative charges right next to each other.
I can charge up the capacitor to 1 volt. It has 1 Coulomb in it.
It'll go boom.
It doesn't go boom.
Okay.
10 to the 19th electron is a lot of electrons. I don't think
that's only 10 to the 19 electron volts.
10 to the 19th electrons would be...
That's 10 to 19 EVs.
That's 10 to the minus, that's
not a lot of energy. It's a nice bang, but it's not like...
Yeah, it's a bang. Yeah, no, I don't mean it would explode the world. I mean it would make a nice little explosion. Nice little pop.
You have to do something with it. As I say, you go to Fry's and for $1 you buy a 1 farad capacitor and you charge it up to a volt. And you've got a Coulomb sitting right there on your desk.
You've got 2 coulombs.
You've got no coulombs. You got 1 coulomb of positive charge, 1 coulomb of negative charge next to each other.
Are you saying there's no energy in the capacitor?
No, there's energy in the capacitor. But the energy in the capacitor depends on the distance between the capacitor plates.
So those plates are apart.
If you were to take the capacitor plates far away, you would make a big energy.
Yes.
I was objecting to your saying that a Coulomb of charge in your desk is something to be afraid of.
A Coulomb of charge uncompensated by a Coulomb of opposite charge would be I think that would be fairly dangerous.
Yeah, move on. Who cares?
Yeah. Capacitor has two plates, positive and negative. They cancel each other. Let's put it this way: if you were to take a cubic centimeter of water, a coulomb of charge is 10. I think it's about 10 to the 19th electrons. That would mean like something like about 1 part in 10 to the 4th of the atoms had been ionized. That would be 10. Okay, so 1 part in 10 to the 4th of the atoms, 10 to the 23rd atoms, 10 to the 19th electrons. That would mean 1 part in 10 to the. So that would be 10 to the 19th electrons. That would be 10 to the 19th electron 10 to the 20th electron volts about. Ionizing one hydrogen atom takes about 10 electron volts. So that would be about 10 to the 20th electron volts. How bad is 10 to the 20th electron volts? Well, it's actually not that bad, but it's, it's a noticeable perturbation. It's a noticeable perturbation. 10 to the 20th electron volts is like the highest cosmic ray energy that can hit you.
It's 100 million TeV.
100 million TeV, right. But only one particle. It's not like an accelerator beam hitting you. So it's one particle with 100 million TeV. That's about the highest energy cosmic ray. So if you get hit by a high energy cosmic ray, it can do some damage. You're right, it's not a big explosion. But I think it's an unpleasant event taking place in your body. Anyway, let's go on. All right, now let's come to energy. Energy and momentum. Energy and momentum are also conserved quantities. They're like charge in that respect. They're conserved. But energy and separately momentum themselves, not their currents and not their flows or not their densities, but the total energy and the total momentum of a system are not scalars, are not invariants. This is more or less obvious. If I have an object here standing at rest and I tell you that it's energy, and remember, keep in mind E equals mc squared, so M and E are similar things. Okay, this object has a certain amount of energy, namely its mass times c squared. And now somebody's going on a really fast railroad train going past it. They will see the mc squared plus the kinetic energy of the eraser. So energy is not something that all observers will agree about. Total energy is not an invariant. It's not a scalar. Neither is total momentum. I say the momentum of this is 0. You going by in the railroad train will say the momentum is not 0. So energy and momentum are not, they are conserved, but they are not invariants. And together, the energy and the momentum of a system also form a 4-vector. All right, we've gone through this when we studied relativity more than once. The energy of a system, again, speed of light equals 1. The energy of a system and the momentum is a 3-vector. It has 3 components. The energy and the momentum of a system together form a 4-vector. The energy being the time component and the momentum being the space components. So you can, if you like, think of the energy as the time component and the momentum, x, y, and z, as the space components of another 4-vector. But this time, it's not the 4-vector of density and flow. The total quantity of momentum or the total quantity of energy of a system together form a 4-vector. The 4-vector is conserved. Each component of it is conserved.
Each component?
Yes. The x component of momentum is conserved. The y component of momentum is conserved. The energy is conserved. So there are 4 separate conservation laws. Okay. Now, again, energy conservation and momentum conservation would be operationally useless if it was just that energy could disappear at one place and reappear on Mars. It would be operationally useless in this laboratory. So again, there is a notion of a flow of energy. Same thing, a flow of momentum. And it's the same kind of thing. Changes in the energy of a system, of a closed system like this, can only happen if there is a flow of energy or momentum or whatever it is through the walls of a system. And so there must also be a notion of a density of energy and a flow of energy. It's likewise for momentum. Let's give them some names, and then let's see if we can make a guess as to what kind of quantity the density and flow of energy and momentum is. I warn you now that I am setting the speed of light equal to 1, so some of the formulas may differ from elementary textbooks in which there are speeds of light floating around. You can always restore the dimensions by making the dimensional analysis consistent. But all right. Energy. First of all is a notion of the density of energy. Energy in a volume divided by the volume, take the volume small, defines a quantity which is the density of energy. Let's give that a name. Energy is the time component of something. Remember, energy and momentum form the 4-vector P0, P1, P2, P3. So first of all, it's a density of something, and let's label this quantity by who it is we're talking about. We're talking about energy, and energy, I'll simply use a shorthand notation, the time component of the 4-vector. So energy is a time component of something. This T is going to be the analog of a density. It is a density. It's the density of energy. But let's go back over here. Where is it? Yes, up here. Notice that the density itself, quite apart from whatever it's the density of, the density is also the 4th component of something. So this is the density of energy is the density of the 4th component. In other words, it's the 4th component of a 4th component. It's the 4th component because it has to do with energy, and it's the 4th component because it's a density. All right? It's the 4th component because it's a density, and density is like the time component of a flow. So we'll give it 2 zeros. 2 zeros because it's the 4th component of a 4th component. Now, what about the flow of momentum? If we were talking about charge, the flow of momentum in the x direction would be called J1. We're now talking about the flow of something whose name is naught. Just to label the fact that we're talking about energy, we put a naught there. But it's a flow of energy in the 1 direction. So we need to put a 1 there. T01 is the flow of the 0 component of the energy momentum 4-vector, in other words, the energy, along the x-axis. How about what would T02 mean? That would be the flow of energy along the 2-axis, and so forth. Okay, that takes care of energy and its flow. What about the x component of momentum? The x component of momentum is just another quantity which is conserved. We ought to give its density a name. How much x component of momentum is in this volume? Well, I don't know how much is. It depends on the microscopic particles. But if there was a flow of particles through the volume, there might be an x component to the... All right, so let's talk about the x component of momentum. What should I call its density? Right. This indicated it was a density. This indicated it was the energy. All right, so now let's write a t, which this index is now 1 because we're talking about the x component of momentum, but we're still talking about its density. So the first index tells us who we're talking about. The second index tells us what direction the flow is in. The flow is in the time direction. It's a density, so this is the density of x component of momentum, the amount of x component of momentum in a volume. How about the flow of x component of momentum? Can you imagine a flow of x component of momentum? Yeah, that's easy. I mean, you just have some particles going along. They have x component of momentum, and moreover, the x component of momentum is flowing. So, along the x-axis. This becomes T1 because we're talking about x component of momentum, but now we're talking about the flow along the one direction. How about a flow of x momentum along the y direction? Does that make sense? Well, supposing I had, all right, there's my x-axis, there's my y-axis. Supposing I have a bunch of particles moving off in an oblique direction. They are carrying x momentum from one value of y to another value of y. A bunch of particles going off that way are taking, they also have some y momentum, but in particular they have some x momentum, but that x momentum is being transported along the y-axis. So yes, it does make sense to talk about the transport or the flux or the flow of x momentum along the y-axis and along the z-axis. Okay, what comes next? Well, the next thing that comes is the y component of momentum. The density of the y component of the momentum is T20. And then the flow along the one axis, T21, T22, T23, and finally T30, T31, T32, T33. These are the four sets of objects, 1, 2, 3, 4, each composed of four pieces itself, which represent the flows and the densities of the components of energy and momentum. This whole object is a tensor. Now, is it obvious that it's a tensor? No, it's not obvious that it's a tensor. We will have to do some more work to convince ourselves that it ought to be a tensor, but it's called the energy-momentum tensor. And we can write it in the condensed notation T mu nu.
Isn't it obvious that it's a tensor because it's a physical thing?
Yeah. Yeah, I would say that that's, I guess the right way to say it is it better be a tensor or else it's not a physical thing. So.
And you write it this way because each component is conserved, unlike the charge equation.
Yeah, well, first of all, this in itself doesn't say that each component is conserved. It just says that they exist. Now we can ask, what does it say to say that they're conserved? Okay, so let's make our best guess as to what it would say that they are conserved. Let's look at the energy. What I want to do is write down, for the energy itself, which is just the first row here, I want to write the analog of the continuity equation. In fact, I'm going to write the continuity equation. The first index here, that's completely passive. It just says that I'm talking about energy. The second index tells me whether I'm talking about density or x or y or z component of flow. Okay, so if I just mimic or just parrot the top equation there, mimic the top equation for energy, what will it say? It will say that the derivative with respect to t.
Why don't you parrot the bottom line?
I will. I'll do all of them. All right, but it says the derivative of t of the energy density plus the derivative of x with respect to the flow along the x-axis plus the derivative with respect to y of t naught y. I'm getting tired of writing them, but you see the pattern. I guess we could call these 1, 2, and 3. Equals 0. All right, now I could do the same thing for the next line. The next line is also it refers to a conserved quantity. It refers to the x component of momentum. The only way the x component of momentum can change in the room is if x component of momentum flows through the walls of the room. Same deal. So we will write the same equation, except wherever I see naught, in the first entry, I will write 1, then naught, and so forth and so on. I'm getting a little tired of writing it. D by dx, t11 plus d by dy, t12 plus d by dz, t13, no, t13 equals 0. And likewise for the third, there are 2 more equations like this. Each one of these rows has a continuity equation associated with it. Now, I can also write this in a single common notation like this, and it is just of exactly this form, d by dx mu of t nu mu equals 0. Nu here is the index which tells us what we're talking about. Energy, or first component of momentum, or second component of momentum, or third component. In other words, it just names the quantity we're talking about. It's the mu index here which tells us which direction we're talking about and gets combined with a derivative here. That's the conservation of energy equation, a local conservation of energy in special relativity. You say, why special relativity and why not general relativity? The answer we'll come to next time. The equation is slightly modified in general relativity. The way that it's modified is the derivative becomes covariant derivative. You say, why not covariant derivative over here? We'll come to that. We'll come to it. It is covariant derivative. Some slippery trickery happens here that doesn't happen here. But this is the basic idea of energy momentum conservation. Okay, so now we have the basic ingredients for the general relativity. We have geometry, which represents gravitational field, and we have energy and momentum, which represent the source of the gravitational field. Normally, we think of the source of the gravitational field as mass, but E equals mc squared. So if c is equal to 1, energy and mass are the same thing. So it's natural to think of mass as the source of the gravitational field. But on the other hand, energy or mass comes together with these other things called momentum. If energy is the source of something about the gravitational field, then in some other frame of reference where energy gets mixed up with momentum, momentum will become the source of some piece of the gravitational field. So Einstein's job was to figure out how to write tensor equations which expressed the sense in which the gravitational field was sourced by energy and momentum, and to write them in a way that made good sense in any frame of reference. We're not going to do that today. That's a little beyond what I wanted to do today. I did want to do one more thing today. I don't know, are we really shot, or is there time for... All right, one more thing we'll do. Now we're coming... I've set up the basic ingredients for thinking about energy and momentum as the source of the gravitational field. All it will take is an equation which has on one side something to do with the geometry. What's it going to be? It's going to be the curvature tensor. The curvature tensor on one side, and on the other side of the equation it will be the energy and momentum. Curvature caused by energy momentum. That's half of the story. That tells us how energy and momentum curves space. The other half of the story is what geometry does to the motion of particles. I want to spend a little bit of time on that, and because I don't want to have to do it next time, although we'll probably wind up going through it the next time. The basic rule that Einstein settled on for the motion of particles, through a gravitational field is that they move on geodesics. They move in the simplest possible way. Particles have little steering wheels, but the steering wheels are locked in the straight ahead direction. But not just in space, but through space-time. Space-time has a geometry. It's described exactly the way we've described it up till now, with a metric tensor, a curvature tensor. Well, the whole story goes through. And particles move through space-time on space-time geodesics. That was the principle, a very, very simple principle. What would it say in flat space-time? In flat space-time, it would say that particles move through space-time on straight lines. That has two pieces to it. It first of all means that they move along trajectories in space which are straight, but it also says that they move with a constant velocity. A straight line in space-time is something which moves in a fixed direction, but with a fixed speed. So the principle that a particle moves on a geodesic in flat space-time would just say that an object moves with no acceleration. Now, of course, that's ignoring all the other kinds of forces in the world, but if all we had was gravitational forces, that would be correct. What's the analog of that more generally? More generally, the statement is that particles move on geodesics, the straightest possible paths. Let me remind you what the equation for a geodesic is. It's just the equation of zero covariant derivative of the tangent vector. The tangent vector is dx mu by d tau, tau being proper time along the trajectory. That's the tangent vector. And to differentiate it with respect to tau, now we have a tangent vector. Along the curve, the tangent vector is doing whatever it's doing. And now we're asking how the tangent vector changes as we move from point to point. Well, that's another derivative with respect to tau. But that's not the covariant derivative of the tangent vector. The covariant derivative of the tangent vector involves the Christoffel symbol. And it's plus gamma mu, nu, sigma, tangent vector dx nu by d tau, tangent vector dx sigma by d tau. This tells us what the orbit of a particle is in space-time. It's a differential equation telling us, in terms of the Christoffel symbol, what the motion is. Now I want to restrict myself. We have 5 more minutes. I'm going to go through this again, but I want to do it now to give you some food for thought. Supposing we're in the limit where Newton is almost exactly right. What does that mean? It means that the gravitational fields are not too strong, and it also means that things are moving slowly. All right? It means that everything is moving slowly. In fact, I'm beginning to move slowly. I think we're going to come back to it next time. I think we're too close to the, yeah. All right. If you want to play with this a little bit, see if you can see what this says. Here's the goal. Put in the fact that all the particles are moving slowly. Okay? That means that dx by dt, not d tau, but dx by dt is small. That the ordinary velocities of particles are small. Are there any components of dx by d tau which are not small? Yeah, the time component, because the time component is almost exactly equal to 1. It's essentially dt by d tau, almost equal to 1. So when particles move slowly, only the time components of these tangent vectors are appreciable. Right? Now, tau and t are almost the same if particles move slowly. So this is almost the ordinary acceleration. This is almost the ordinary acceleration. On the right-hand side here, these things are either very small or they're close to 1. So what does it say? It says the acceleration is equal to the Christoffel symbol, to a certain Christoffel symbol. The Christoffel symbols evidently are the gravitational field, the gravitational acceleration. They're like the things we called in the beginning A, the field of acceleration. So this is the connection. Here's how we're going to make the connection between Newton's equations, Newton's second law of motion, and Einstein's principle that things move on geodesics. These are negligibly, they're essentially one when this is time components, and the gamma becomes, which gamma is important here? What are the relevant indices here? Remember that dx by d tau is only appreciable if it's a time component. So that means that the gravitational force is basically just gamma mu 0, 0. The gravitational force along a given direction, let's say the y direction, is the Christoffel symbol gamma y 0, 0. That's going to be the link to guide us to the motion of, well, to the connection between various gravitational things and other things in Newton's equations. We might as well write it down right now. The field of acceleration is equal to the Christoffel symbol. We'll come back to that, and then we'll try to put the whole thing together and find equations which express the connection between the gravitational field and the masses on the one hand, and the gravitational forces on particles on the other hand.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.